Hello everyone, welcome to this short recap session for the course Analog Microelectronic Circuits. In this session MOSFET lessons are revised. Our first lecture was on the discussion of MOSFET and its types. The two types of MOSFET are depletion and enhancement type MOSFETs. The enhancement type is a normally off device is the one we discussed in rest of the lectures. Understanding the structure of MOS with respect to its substrate is also very important. The figure shows the lateral view of MOSFET to understand the width, length and its oxide thickness. The fourth terminal of the MOS is also shown in figure. Usually for an N-channel MOS body is connected to the least potential available in the circuit and for a P-channel MOS for the highest potential available. It is for the simple reason that the p-n junctions in the structure remain reverse biased. Channel formation is something we should understand in MOSFET in particular. As a negative gate voltage is applied, free carriers in the substrate get accumulated under the gate region. As we increase the gate voltage to a higher positive voltage, negative charges from source and drain regions will fill the region beneath the gate causing an inversion. This inversion channel aids in current conduction when we apply a VDS. The value of VGS at which the inversion happens is called threshold voltage, and for an NMOS it is positive. When VGD equals VGS, the channel formed will be uniform and a current will flow linear. But when a higher VDS voltage is applied, VGD reduces. This will not attract the charges at the drain region, results in tapering of channel at drain end. At VDS equals VGS minus VT, the channel at drain end pinches off and current will saturate. These are the conditions for regions of operation of a MOSFET. For an N-channel MOSFET, VGS should be greater than threshold to turn on the device. Then depending on the value of VDS, the device may either in linear or saturation region. These conditions and the corresponding drain current will help in solving all numerical related to MOSFET. The condition VDS equals VGS minus VT is called edge of triode or edge of saturation region. Now in the case of a non-ideal MOSFET or practical MOSFET, a finite output resistance will be there in saturation region. That means there will be a slight increase in current in saturation, because drain current increase with increase in applied VDS. This is called as channel length modulation and is depicted in the figure. The length of the channel is changed from L to L minus delta L. The practical MOSFET has an output resistance equal to 1 by lambda its set. This slide shows the IV array of various elements like resistor, ideal voltage and ideal current sources. These array will be familiar to you all. Now look at the fourth diagram where the array of a current source in parallel to a resistance is drawn. The array looks like that of the practical MOSFET in saturation. Now for every analysis, we need a suitable model for MOSFET. Representing MOSFET in terms of known elements can be a useful model for amplifier analysis. The figure shows the ideal MOSFET model in saturation. MOSFET is represented as a voltage-controlled current source. Further, by including output resistance in saturation, the model of a practical MOSFET can be as shown in figure by adding a resistance in parallel to the current source. MOSFET can be used as an amplifier in saturation region where it acts as a controlled current source. The figure shows the three amplifier configurations: common source, common gate and common drain. In each configuration, one terminal, either source or gate or drain, will act common for input and output signal. Intrinsic gain of MOSFET is the maximum gain available from a MOSFET, and it can be understood by loading a MOSFET with an ideal current source. The intrinsic gain of MOSFET is expressed in terms of GM and ρ, and can be further obtained in the form of early voltage and overdrive voltage. This is a very useful expression. The transconductance of MOSFET is an important parameter of MOSFET and can be expressed in three ways, which shows their relation to various parameters. When we approach any numerical related to amplifier, the easy and systematic way is to divide the analysis into DC analysis and AC analysis. Find DC current. Using DC current, find the small signal parameters. Then draw the equivalent circuit and find small signal gain and resistance. Maximum allowed input signal to an amplifier can also be obtained by writing the saturation condition including both DC and AC voltages. Calculation of output resistance is an important tool which will help in finding the gain of any circuit. The standard procedure to find the output resistance is listed. The steps are carefully executed to find the resistance of any given circuit. The examples for the output resistance calculation are shown here. These are also some useful configurations. When a resistance is connected to the source of a transistor and the resistance calculated from its drain will be a magnified version of the resistance by intrinsic gain of the transistor. This slide shows the summary of all the parameters of the amplifiers discussed. Gain, input and output resistance for cases with and without channel length modulation is listed. Knowing these formulas will definitely boost your confidence while solving numerical questions. The conditions of PMOS transistors are also important to understand. Since the VGS required for a PMOS is negative, when VGS less than threshold, device turns on, and when VGS greater than threshold, device turns off. The condition for linear and saturation regions of PMOS are listed. The conditions are same in all aspects except for the condition is reversed for linear and saturation. Finally, the equivalent circuit of PMOS is similar to that of NMOS and the same model can be used in all the circuit analysis. Hope this short session helped you in revising the lessons learned in class. Have a wonderful learning. Thank you.